So just kind of a recap. Remember, we've been solving matrices, and what's been kind of our systematic plan? Like, where do we start in general? Where do we start trying to fix the matrix? We start with column 1, right? And we fix which one of the things first, the ones or the zeros? The 1 first, and then followed by the zeros, right? And then we move on to column 2 and do the same thing. If there is a column 3, we do the same thing for that too, right? So just to kind of hopefully remind you about that, but let's look at, so I'm just going to say continued solving systems using matrices. Because we're going to do a little bit more of section 4.2, but then we're actually going to do some 4.3 kind of mixed in there too. Who took good notes? Like, what example number were we on last time? 11. Oh. That makes it seem super long, but we did spend 3 days on this. All right, so let's say that I told you to solve using a matrix. And this was the system. We're going to do a 3-variable system, so make it like 3 lines long. So let's say the first equation is this. The second equation looks like this. And then finally the third equation. So remember what I said last class. The first thing that you want to do when using a matrix is make sure that you write down the numbers correctly to begin with. Okay. So let's pull the numbers and write them in an augmented matrix form first. And then we'll start to decide maybe what changes need to be made. Okay, so the first spot that we need to start with is this spot, right? Now notice, remember at the first we can either do a row swap or we can multiply by the what of that number? The reciprocal of that number, right? And notice that's actually going to probably work better than a row swap. Notice, will a row swap get us anywhere? There's no ones anywhere, right? So that's not going to help us if we do a row swap. So we need to remember that we want 1 here. Okay, so you need to make sure you're stating what rule you're using. Okay, notice I want to do 1/2 of row 1. So what's not being changed? What 2 things are not being changed? Row 2 and 3. Okay, but we're just finding half of everything in row 1, which won't be so bad. We won't even get fractions. So this will be 1, 1, -2, and then half of 0 still 0. Okay, so we're good there, and now we move on to these, right? What do we want there? We want zeros. So we're going to do 2 different instructions. Okay, that'll get us the zeros where we want. So we're going to do, what number is going to cancel out a 2? A -2, right? So we're going to do -2 row 1 plus row 2, and remember we're going to send that to row 2. Okay, for this textbook, they like to use the arrow notation there. So I'm going to make this negative sign a little more prominent. And then what do I need to add to -2? The opposite, right? So I need to do 2 times row 1 plus row 3, and I need to send that to row 3. Okay, so which row's not changing? We're not sending anything to row what? Row 1, so we'll pull that over. And then we'll just be careful, right? It's -2 times row 1. So like I like to visually point at each little pair. So it's -2 plus 2, which is 0. -2 plus 3, which is 1. -2 times -2 is 4. Plus this would be 3. And then lastly for this instruction, -2 times 0 is 0, right? Plus 4 would still be 4. Okay, so now the second instruction says twice row 1 plus row 3. So 2 times 1 plus -2 is 0. That's actually why we chose those instructions, right? So we should get a 0 there. 2 times this plus this would be 5. 2 times 1 plus 3 is 5. 2 times -2 is -4, plus 1 is -3. And then lastly, 2 times 0 plus 2 would be 2. Okay, so what do we notice is complete then? Column 1's complete. Okay, so we're going to move on to what? Column 2, okay? But notice we actually get something here for free, right? Sometimes that happens, okay? So notice the middle number is already what we wanted it to be, and that's what we would have tackled next anyway, right? We would have tried to find the 1. So then what do we go to since the 1 is good? The zeros, right? So right here, I want zeros. Okay, so I can say this in some different ways, but what could I add to a 1 that would make it a 0? Negative 1, right? So I'm going to do negative row 2 plus row 1. And where do I want to send that? To row 1, because that's the row I want to change. Okay, what number would cancel out of 5? Negative 5, so I'm going to do negative 5 row 2 plus row 3, and I'm going to send it to row 3. Okay. Notice, by the way, that I tend to use the row with the 1 in it, okay, the one that we already placed or that we got for free in this case, because that's really easy to use, right, because something times 1 ends up being itself. Okay, so you usually use the row with the 1 in it to change the other 2 rows. So row 2 is not changing, right, because we're not sending anything to row 2. Okay, so we're just going to go negative row 2 and then plus row 1. What's negative 0 plus 1? 1, right? By the way, if something gets messed up that you already placed, you did something wrong. Okay, this method is kind of guaranteed to not mess up what you already did. Negative 1 plus 1 is 0, just like we wanted. Negative 3 plus negative 2 would be negative 5. And then negative 4 plus 0 would be negative 4. Okay. Then lastly for this step, negative 5 times row 2 plus row 3. So 0 and 0, that's not rocket science, it's just 0. Negative 5 times 1 plus 5 is also 0. That's what we wanted. Negative 5 times 3 is what? So we're doing negative 5 times this row plus this row. So negative 5 times 3 is negative 15, right? Plus negative 3 is what? Negative 18. Okay, so don't get thrown off if you have bigger numbers. That's all right. And then lastly for this step, negative 5 times 4 is negative 20. Plus 2 is also negative 18. Okay, so notice in our little matrix puzzle, we are 2/3 of the way done now. We have 2 columns out of 3 completed. Okay, so we move on to column 3, right? Specifically, which number do we tackle next? The one in the bottom corner, right? What do we want this to be? We want this to be a 1. Okay, so yes, I know the number is large, but how do we get a 1? So positive 18, if we added that, that would make it a 0, and that's not really quite what we want, right? So what do we want to do instead? Yeah, we want to use the reciprocal, and who cares that it's a big number? We're just going to say negative 18, or negative 1 over 18 times row 3. Essentially, you're just dividing by negative 18. So notice, I'm not changing rows 1 and 2, so I'm going to pull them over. And then the zeros stay zeros, right? Because no matter what you multiply times 0, it's 0. But then what do you get in both of these spots then? 1. So we're actually almost there, okay? So the next thing is we just need to change these to what? Zeros. So I'm going to do it down here because I don't think I'm going to have enough room. So I want to do 5 times row 3 plus row 1, and I want to send that to row 1. Okay, why did I use 5? Because what's the number I'm trying to eliminate or make a 0? Negative 5, right? So I'm going to use negative 3 here. Okay, so notice, again, I used where the 1 was located in that column, right? So I used row 3 in order to make the other numbers what I want. All right, so final step, and then we'll have it in reduced form, so we'll be able to tell our solution. So 5 times 0 plus 1 is 1. 5 times 0 plus 0 is 0. 5 times 1 plus negative 5 is 0. Notice those are all what we wanted them to be, right? Maybe we should just pay attention to the final step, though, especially, okay? So 5 times 1 plus negative 4, so 5 plus negative 4 would be 1. Okay, same thing here. If you do negative 3 times 0 plus 0, it's going to stay 0. Negative 3 times 0 plus 1 is going to stay 1. Negative 3 plus 3 is going to be 0. But then it's maybe here where I need to pause, right? So negative 3 times 1 plus 4 would be 1. Okay. So the solution ends up being what kind of nice answer? 1, 1, 1. And then, of course, don't forget, I didn't mention this with 3 variable systems, but how could you make sure this is right? You could check this by plugging in this answer to all 3 of the equations, right? It should work for all 3. So I'm going to say check by plugging in this solution to all equations. Okay, so just for time reasons, we're not going to do that, but I'm just saying you should be able to kind of check these and know for sure that you did it right. Okay, so I want to look at maybe some special cases to make sure that we remember how to do those. I think I talked about those a little bit on Friday. So I just want to make sure that we kind of remember. So remember there were 2 special cases. Okay, the first one was no solution. Some textbooks call this inconsistent. Okay, so if you see the word inconsistent, it means the same thing as no solution. Okay, so I'm not going to describe this a lot, but this is where you get zeros on the left in a row and something else on the right. Okay, so like you get 0, 0, 0, and then a 2, okay, or something like that. And then the second special case was infinitely many solutions. So the other word that a lot of texts tend to use, so we didn't talk about these words on Friday, but another way to say infinitely many solutions is dependent, meaning that it's dependent on the situation, but there are actually a lot of answers. And remember, this is when you get zeros in a whole row. Okay, so notice like how close they are, right? They're really, really close. No solution is when you have all zeros except the number on the right. And then infinitely many solutions is when you have just all zeros all the way across. Okay, so they're super, super close, and I'm hoping that you'll remember kind of what that looks like. Okay, so we kind of did some of these with 2 variables, but I want to touch on it for 3 variables. So without solving a full matrix, I just want to say what would happen if you get to the bottom of the matrix and it looks like this. So you're going along. Sorry about that. Let me move that up. You did all your steps. You're certain that you did them right. You got everything placed correctly. But when you got down to the bottom, you weren't able to get the 1 where you wanted. Okay. By the way, there's no way you're ever going to get a 1 here when it's a 0, because anything times 0 is just going to stay 0, right? So you can try all you want to multiply that row by something, and it's never going to give you what you want. So what do we notice? There's basically 1 row that's off, right? Or 1 row that indicates a special case, okay? And we talked about this on Friday, but let's go ahead and write it out. The reason why this is no solution, because that's what it is because this is impossible. You cannot have 0 times x plus 0 times y plus 0 times z equal anything other than 0. Okay, so what do we say about this then? No solution or possibly inconsistent. So you just need to be able to kind of use those words interchangeably. On test 1, I'm okay with you using either terminology, okay? But on your homework, you might see them mismatched. Notice, I think it makes sense that this means no solution because the prefix "n" means not, right? So not consistent kind of means the same thing as no solution. So I think you can kind of remember it that way. All right, so what about if you get something like this? So this is where I want to spend some more time. The infinitely many solution scenarios are more difficult to describe. Okay, so let's talk about what our normal method would be, right? It looks like if we were working this problem, we fixed column 1 because it looks good, right? And then we moved on to what? Column 2, and it looks good. But then we get to column 3 and we're like, I can't do anything, right? Because this is where we would go next, right? What would we want right here normally? A 1, and we can't ever get it because what's anything times 0? 0, so it's just going to like perpetually stay kind of not all the way fixed. So this is reduced. It's just as far as we can go. Okay? It may not be as reduced as nicely as you would like it to be, but it's reduced as far as this one goes. So let's talk about what's left. So we have x plus 2z equals -3 if you read the first row, right? What about the second row? Y plus what? 3z equals 4. And then the last row is not something that ruins the whole thing. It's just something that doesn't help us, right? Why do I say it doesn't help us? Because would it matter what x, y, and z are, really? No, like 0x plus 0y plus 0z, no matter what those three numbers are, is always going to be 0. So we don't get something that throws the whole thing out. We get something that's just not really all that helpful. Okay. So I do want to say that this is dependent. And remember, or that means infinitely many solutions. I can't spell infinitely, apparently. But I want to talk a little bit more about what those solutions are, which we did not do last lesson. Okay, so it's fine to say that it is dependent or infinitely many solutions, but infinitely many solutions doesn't mean all solutions. There's a difference. All solutions means any combination you could dream up works. Infinitely many just means there's an infinite number that work. Okay. So it's not just any old point, it's actually very specific points, okay? So with infinitely many solutions, we're going to make sure that we describe the solutions. And so the solutions are going to be any point that follows this pattern. Okay, so we just need to figure out what x, y, and z are. So maybe off to the side, let's talk about the first equation. So we have x plus 2z equals -3. Okay, so what I'm going to do is I'm going to solve for x. So if I subtract z from both sides, I get -3 minus 2z. Okay, so in other words, if I want an x comma y comma z, my x can be described as this pattern. Okay, and we're going to talk about what that means in a minute. Okay, all right, so let's go on to the second equation. The second equation is y plus 3z equals 4. And it is going to be able to be solved for y, so we're going to subtract 3z from both sides. So an expression that describes y is 4 minus 3z. And then z is just going to be any number it wants to be. So it's been a minute probably since you've had Algebra 1 in high school, but essentially this is your independent variable, and these two variables are dependent on z. Okay, so in other words, z is allowed to be anything at all, but once you set z, then x and y have to follow a pattern based on what z was. Okay, so we're going to circle this, but then we're going to list some possibilities for solutions. So this isn't going to be a full list because we can't list them all, because how many are there? Infinitely many. Okay. So what I mean by z can be anything is you can just come up with anything you want z to be. So let's say that z is 0. So I'm going to put 0 in for z, but once z is set at 0, aren't x and y solidly set also? In other words, if z is 0, what is x going to be? What's negative 3 minus 0? Negative 3. And then if z is set here, what's y going to have to be? 4. Okay. But we could set z at anything we want, right? So let's say z was 1. Okay, and I'm just pulling numbers out of the air. I'm just trying to pick pleasant numbers. So if z was 1, what would you get for x? Negative 3 minus 2 would be negative 5. 4 minus 3 would be 1. Okay. So let's do one more. So let's say I just decided to make z 10. Okay, because I can make z anything that I want to. Z is independent. But once I place z, it automatically sets x and y, right? So what's negative 3 minus 20? Negative 23, right? If I put a 0 or 10 in here, I'm going to get 4 minus 30, which is negative 26. So I'm going to say or ... because I could keep going here, right? And what am I kind of constantly changing? Z, and then what does that automatically set then? It sets what x is. Okay. So just remember that there are actually infinitely many solutions here. And that's why we said ... Okay, so let's look at a couple more, and then we're going to see if we can look at maybe some more unusual matrices. By the way, this thing that I'm doing here with these example questions where I'm not making you solve a full-blown matrix, I'm just giving you an already completed one and asking you to tell me a conclusion, is probably something I'd be most likely to do on test 1, because how long do these 3 variable matrix problems take? A minute, right? They take a long time. Okay, so I'm much more likely to put one that's already almost done or already completely done and just tell you that I want you to tell me what the conclusion is. Okay, so these are pretty similar to what I plan to do on test 1 to kind of save some time. Okay, all right, so notice we have everything kind of set where it's supposed to be, right, for column 1. Column 2 doesn't look quite right. Okay, so if I gave you this and I asked you to finish it out if you could, what could we do so that column number 2 would be right? So couldn't we row swap row 2 and row 1, or sorry, row 2 and row 3? Okay, wouldn't that give us the pattern that we're really looking for, at least so far? So this would be 0, 1, 2, 0, right? And 0, 0, 0, 0. Okay, so generally speaking, we don't want to do a row swap in the middle because it might mess up what we just did, but notice that row swap doesn't mess up our zeros, right? So we're good to go. All right, so now we would normally move on to this one, but what do we notice? This one doesn't work, right? So what does that mean then? Like right off the bat, what do you know about this solution? It's infinitely many because of the 0, 0, 0. Well, so it's going to be infinitely many solutions. And so we also need to describe what the points will look like. So let's talk about what we have. Okay, the first row actually gives us x. X is negative 1. So x is not in question in this answer. It's always negative 1. But y is not set in stone. Y plus 2z has to be 0. And then notice this is just kind of almost a dummy line, right? Like it just doesn't help us. So without showing too much steps here, if I just solve this equation for y, okay, then what is x set at in this pattern? X is set at -1. Notice I didn't get an equation for x in this case. What about y? The pattern for y is going to be what? -2z, because we moved the -2c over. So if you want to show that separately, you can, but I know that's actually not great to see. I really hate the lighting with this document camera. It's not so good. That's a little bit better. But we moved the -2z over, right? And then z is just the independent one that can freely change. Okay, so if you want to describe it, this is your x, this is your y, and this is your z. Okay, but there's still infinitely many solutions that can be listed in this format. We'll move that over. It's just that with this infinitely many solution system, what is x always going to be? -1, but z and y are still changing. Okay, so it's like -1 is set, but the y and z are different every time. Okay. Okay. So one more where it looks completed and we have to figure out what's going on with it. So notice if you're thinking about like what we would do, column 1 is good, but we try to fix column 2 and notice nothing's going to work. Why not? This is going to stay a what? A 0, and even if you row swap it, it's never going to be 1, right? Like we're stuck. That's as far as we can go, okay? So let's talk about what we have. We know that x is 7, right? And we actually know something about z, right? We can actually work it out. We know that 4z equals -3. So how could I get what z is actually? Just divide by 4, right? So I end up getting that z is -3/4. So what's the only thing that isn't really talked about? I know what x is. I know what z is. What's not talked about? Y isn't talked about, right? So this is dependent, or infinitely many solutions. But kind of like the last one, some of my values are set. And it's also any point that looks like this, right? X is set at 7. Z is set at -3/4. But y can be what? Y can be anything at all. So we're just going to call that, in this case, y, right? In other words, y can be any number you want to. So an example of a solution would be 7, 0, -3/4, or 7, a million, -3/4, or 7, -2, -3/4, right? So the 7 and the -3/4 are set in stone, but what's not set in stone? The y, right? And we still have infinitely many of them, okay? So those are kind of all the ways that infinitely many solutions might look when you encounter them, okay? Okay, so let's look at some solutions, or some systems rather, that maybe aren't perfectly square. And let's see how we're going to tackle those. So let's say that I wanted you to solve the following system using a matrix. Yep. So notice it almost looks like we're missing a row. It almost looks incomplete, but we're going to do the best we can with the information that we have. We're just going to start our process and kind of work our way over and see what we can get. So we're going to set up the matrix just like it looks. So it's going to be 1, 2, 3, and then a bar, and then 5. What do you think we're going to put in the spot of x since there isn't anything in the x spot? We're going to put a 0, and then there's going to be a 1, -5, 0. So I know it looks almost like we're missing a row, but we're just going to go with what we have. Okay. So notice, what's our systematic process? We like to start with column number what? Column number 1, right? But notice column number 1 is actually good, like as far as we have of it, right? Like 1, 0 is the right pattern, so we're good to go. Okay, so we move on to what then? Column number 2, okay, but actually that's where it should be also, right? Like if you diagonally start from the left and go down, then that should be a 1, right? So then I can move on to what? This, right? I want this to be a 0. So we're just going to go as far as we can and see what we get here. So what do I want to do then? So I want to do -2 times row 2, right, plus row 1, and I want to send that to what? To row 1, right? I want row 1 to change, so I'm sending it to row 1. So row 2 is the same. And then let's do our calculation, right? -2 times 0 plus 1, that stays 1. -2 plus 2 is 0, that's what I wanted to happen. And then -2 times this is 10, plus 3 is 13. And then -2 times 0 is 0, plus 5 is 5. So notice, we're good here, 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 and here. So normally speaking, where would we go? If there were another row here, we'd be here, right? But there's not. Okay, so in other words, we can't go further because what we want to happen kind of can't happen, right? Some people, just so you know, will actually just fill this in with a row of zeros. Because notice a row of zeros doesn't really change anything, right? But if you really are bothered by the fact that there's not enough equations, you can add that row. But notice in that case, this will never be a 1, right? So we have to stop here, okay? So notice we have to stop since we can't go further. Okay, we'll never get a 1 where we want to get a 1. So in this case, we're just going to read what the row, so I'm going to rewrite this just because I wrote something beside it. So this is what I got, right? So I got x plus 13z is 5, and I got y minus 5z equals 0. And if I want to think of it, I essentially got a row of all zeros, right? So then what's my conclusion then? This is dependent, or what kind of solutions? Or infinitely many solutions. And I also want you to say that it's any point that looks like the following. Okay, so I want some description for x, y, and z because they're not random. They have a pattern to them. Okay, so I'll start you off with the easy part. Z is going to be our dependent one. Z can be anything that it wants to be. But then we go back up here and we try to figure out an expression for x, right? So we could subtract 13z from both sides. So what's going to be my expression that would cover all the x's? 5 minus 13z, right? That would cover any x pattern that I could possibly have. What about the y's? Or how can I get it? Go back to the equation that involves y, and what can we do? Add 5z to both sides. So a pattern that would describe y would just be 5z. Okay, and then once again, notice this is an x, comma, a y, comma, a z. Okay, so when you have equations that seem to have not enough equations, just go as far as you can and then come up with your conclusion at the end. Okay, so what about this one? So let's say that I want you to just tell me the conclusion for this one. So notice this one has more rows than it does columns, right? So it's not a square matrix again. So let's just kind of start reading what the rows tell us, right? So what does the first row tell us? X is 5. What does the second row tell us? Y is 7. But the third row tells us something that's what? Not possible? Okay, so if the third row is not possible, then what does that mean about the whole thing? Even though we seem to have solutions for x and y, what are we going to say? We're going to say no solution or what? Or inconsistent. So one bad row ruins everything. Okay. Kind of like in life, right? One bad row in your life ruins a lot of stuff. But let's contrast that with this one. So what if you were to get 1, 0, 5? I'm just going to keep the numbers the same, except the last row is 0, 0, 0. So before we jump and say this is infinitely many solutions, I don't really think this one is, because it's not a perfect square, okay? Because we get the same things for rows 1 and 2 that we did in the previous example, right? But the last example, we get something that's not impossible, but what? It's actually always true. In other words, consider it kind of an extra row, okay? So we actually have a solid single solution here. What is our solid single solution? Yeah, our solution is 5, 7. But notice like how close these two examples are, right? So it really matters what the last row is. It actually matters quite significantly. Okay. So let's do one where maybe I make you solve one that looks like that, and then we'll see what we get. So I want you to solve the following system. So we're going to do 3 equations. So let's say x plus 2y equals 7. And then 2x minus 4y. Hang on, I know what the answer's. What I want the answer to be, so I got to think about it for a minute, equals 10, negative 10. And then 2x plus 4y equals 14. So notice this isn't going to be a square because we have an extra equation. But in a system of equations, we still have to try to find solutions that work for all of them. Okay, so a solution that would work for this would have to be able to work for all 3, even though it seems like we have an extra. Basically, we're just putting a little bit more restrictions on x and y. So first, let's set up our matrix. Okay, now we won't have a z, right? Because we won't have a third column, I mean. So we've got 1, 2, 7, 2, negative 4, negative 10, and then 2, 4, 14. Paper's really slidey today. Okay, so we're going to pretend that we don't notice that we have kind of a missing column this time, right? We're not missing a row this time, we're kind of missing a column. You're just going to do your process as you normally would. Where would be the spot where you would normally start? In the top corner, right? And it's already what we want it to be. Okay, so what are we going to move on to after that? We're going to move on to these two, and what do we want here? We want zeros. Notice they're both the same number, so we're going to do -2 times row 1 plus row 2 and send that to row 2, and we'll do something similar for row 3. So we still need 2 instructions, but they look very similar. Okay, so what row's not changing at any rate? Row 1. All right, so -2 plus 2 is 0, just like we wanted. -2 plus, -2 times this plus -4 would be -8. Careful about your signs, right? That would be -4 plus -4, which is not 0, it's -8. -2 times 7 is -14, plus -10 is what? -24, I think. All right, what about this one? -2 plus 2 is 0, just like we wanted. -2 times 2 plus 4 is also 0, because it's -4 plus 4. And then -2 times 7 plus 14 is also 0. So by the way, that's how sometimes you get a 0, 0, 0. You just do a normal calculation and you end up with something weird. But we're not going to worry about that, because what's the number we're actually supposed to tackle next anyway? It's not the 0 anyway. We're supposed to tackle which one? The 8, right? The -8. And we want that to be a what? We want that to be a 1. So I'm going to point it out in there. That's what we want. So we're going to do -1/8 times row 2. So notice that rows 1 and 3 are staying the same. But row 2, we're basically dividing by -8. So we're going to get 0, 1, and 3. Okay, and then we're almost there, because our next step, notice we kind of get this one for free, right? That's supposed to be a 0, and it already is. So then we work on the very last thing, which is what? The 2, and we want that to be a 0. So what sign do you use for a +2 to get rid of it? Negative, right? So I'm going to do -2 times row 2, where the 1 is, right? Plus row 1, and I'm going to send that to row 1. So rows 2 and 3 pull over. Nothing's getting sent to them. And then let's see what we get. So 2 times 0 plus 1, that's going to stay a 1. -2 times 1 plus 2 is going to be 0. And then lastly, -2 times 3 is -6, plus 7 is 1. So notice this is just quicker than a full-blown 3-variable matrix, right? Because now we don't have a column 3 to move on to, right? We are finished. How do you know we're finished? This is as far simplified as we could possibly get it, right? So now we just need to figure out what we have, right? We have x equals 1. We have y equals what? 3. And then do we have a row that kicks us out, or do we have a row that just kind of doesn't matter? The row just kind of doesn't matter, right? So it doesn't kick us out because it doesn't give us something else on the right as far as those zeros go. So then it's not infinitely many solutions. It's actually just what? Just one solution, and that solution is 1, 3. Okay? Don't forget that you can check this by doing what? By plugging it into which equation? All of them, yes. So check by plugging this in to all 3 equations. So instead of, quitting when it seems like you don't have all the information, just realize that actually when you're missing stuff, it's going to be a quicker process. Okay, you're not going to have as many numbers to change. So try to think of it like that.